Werner Heisenberg's position in Germany before and during the Second World War was not simply that of a talented scientist working within a national system. He occupied a role of extraordinary influence, visibility, and symbolic importance at a moment when German science itself was being violently reshaped by ideology. By the late 1920s, Heisenberg was already internationally recognized as one of the central architects of quantum mechanics. His formulation of matrix mechanics and the uncertainty principle did not merely add to physics. They overturned the classical worldview that had dominated science since Newton. At a remarkably young age, he became a Nobel laureate, a professor, and a global authority on the deepest laws of nature. When the Nazi regime came to power, this reputation made him impossible to ignore and impossible to replace. Germany had once been the undisputed center of theoretical physics. Its universities attracted the brightest minds from across Europe, and its research culture set the global standard. That world collapsed almost overnight after 1933. Jewish scientists were dismissed, exiled, or forced into silence. Entire schools of thought were labeled corrupt, degenerate, or un-German. Quantum mechanics and relativity, abstract and mathematically demanding, were attacked by ideological factions who favored intuition, determinism, and nationalist mythology over empirical rigor. In this climate, Heisenberg became both a target and a shield. Despite being non-Jewish, Heisenberg was publicly denounced by proponents of so-called German physics. He was accused in SS publications of promoting Jewish ideas and undermining Aryan science. At one point, his life and career were genuinely at risk. That he survived this period was not due to ideological alignment with the regime, but because of his undeniable scientific authority and the intervention of influential figures who recognized that without him, German physics would collapse entirely. Eventually, even the SS leadership accepted that Heisenberg was indispensable. This acceptance elevated him into a unique position. He became the primary custodian of advanced theoretical physics within Nazi Germany. By the mid-1930s, Heisenberg was effectively the most important theoretical physicist remaining in the country. Others had fled, been silenced, or were focused on experimental work. He was responsible not only for research, but for education. He trained the next generation of German physicists at a time when intellectual continuity was under severe threat. His lectures on quantum mechanics ensured that the discipline did not disappear entirely from German universities. In an environment where ideology sought to dictate truth, Heisenberg insisted, quietly but firmly, that physics must remain grounded in mathematics and experiment rather than political doctrine. This role placed him in constant tension with the regime. On the surface, he appeared as a loyal German academic, continuing his work under the state. Beneath that surface, he was navigating an environment where every scientific decision carried political implications. Teaching quantum mechanics was not a neutral act. It meant preserving a framework of thought that the regime distrusted and did not fully understand. In this sense, Heisenberg's position was not passive. By remaining at the center of German theoretical physics, he became a barrier against its total ideological destruction. His leadership extended beyond the classroom. When nuclear fission was discovered in 1938, it was inevitable that the German state would turn to its most prominent physicist for guidance. Heisenberg's reputation made him the natural choice to advise and later lead theoretical efforts related to nuclear research. This was not a promotion he sought in a vacuum, it was a consequence of his standing. In the eyes of the regime, he embodied the highest level of German scientific capability. This perception granted him access, protection, and authority, but it also bound him to the machinery of a state at war. Crucially, Heisenberg's influence shaped how nuclear science was understood by German leadership. He was not merely calculating equations in isolation. He was interpreting physics for generals, bureaucrats, and politicians who lacked deep scientific literacy. How he framed possibilities mattered. How he expressed limitations mattered. His assessments of feasibility, timescale, and practicality influenced strategic decisions at the highest level. As Germany's leading theoretical physicist, his words carried weight that few others could rival. Internationally, Heisenberg's position was equally complex. Before the war, he had been deeply integrated into the global scientific community. He collaborated with physicists across borders, spoke the shared language of mathematics, and belonged to a culture that traditionally transcended national conflict. War shattered that culture. Suddenly, Heisenberg was isolated behind political and moral barriers, seen by former colleagues with suspicion or outright hostility. Yet even then, his scientific stature remained unquestioned. Allies did not doubt his brilliance, they doubted his intentions. This dual perception highlights the uniqueness of his position. Within Germany, he represented continuity, competence, and intellectual legitimacy. Outside Germany, he represented the uncomfortable reality that world-class science could exist under a criminal regime. Heisenberg embodied the contradiction between scientific universality and political allegiance. He was living proof that genius does not vanish under dictatorship, but it does become morally entangled. It is important to understand that Heisenberg did not operate as a free agent. His prominence meant visibility, and visibility meant surveillance. Every move, every lecture, every collaboration was potentially scrutinized. Unlike anonymous researchers, he could not disappear into obscurity or quietly refuse involvement without consequences. His value to the regime protected him, but it also trapped him. Leadership was not optional, it was imposed by circumstance and reputation. By holding his position, Heisenberg ensured that Germany retained a functioning theoretical physics community, however diminished. This continuity would later allow post-war German science to rebuild more quickly than might otherwise have been possible. The frameworks, methods, and intellectual standards he preserved did not vanish with the fall of the regime. They survived, contested and scarred, but intact enough to be reclaimed. Understanding Heisenberg's role as Germany's leading theoretical physicist requires abandoning simple moral categories. His position was not one of pure resistance, nor of enthusiastic collaboration. It was a position defined by responsibility without clarity, power without freedom, and knowledge under coercion. He was neither the regime's ideologue nor its innocent bystander. He was its most valuable scientific mind, operating in a space where every equation existed under the shadow of history. This is why the debate surrounding Heisenberg has never settled. His position magnified every choice he made and every choice he did not make. To judge him fairly, one must first grasp the extraordinary weight of the role he occupied. The last guardian of advanced theoretical physics in a nation that had turned against reason itself. Standing at the crossroads where scientific truth, political power, and moral responsibility collided. The moral ambiguity of working under the Nazi regime cannot be understood through simple categories of loyalty or betrayal. It unfolded in a world where survival, duty, fear, and conscience collided daily, especially for intellectuals whose skills were both valued and distrusted by the state. For scientists like Werner Heisenberg, the regime created a moral landscape with no clean exits. Every choice carried consequences, and neutrality itself became an illusion. Nazi Germany did not merely govern, it demanded alignment. The state sought to control not only political behavior, but thought itself. Universities were purged, disciplines were reshaped to fit ideology, and intellectual life was subordinated to racial doctrine and militaristic goals. In such a system, continuing to work as a scientist was never a purely professional act. It was unavoidably political, whether intended or not. To remain was to be seen as complicit. To leave was to abandon students, colleagues, and an entire intellectual tradition to ideological ruin. For those who stayed, the question was never simply, should I cooperate, but how much can I refuse without being destroyed? Open resistance was rare and often fatal. Silent resistance was subtle and ambiguous, indistinguishable at times from self-preservation. Many scientists convinced themselves that by remaining within the system, they could mitigate its worst excesses, preserve knowledge, or prevent more dangerous figures from taking control. Whether this belief was moral courage or self-deception remains deeply contested. The Nazi regime exploited this ambiguity. It allowed non-party members and even ideological skeptics to continue working as long as their expertise served state interests. This created a gray zone where individuals could function without explicit endorsement of Nazi ideology while still benefiting from state protection and resources. The regime did not require love, only usefulness. For scientists, this arrangement was both a shield and a trap. Working under such conditions meant constant moral compromise. Participation in state-funded research, even if not directly related to weapons or atrocities, helped sustain the regime's technological and intellectual legitimacy. Every lecture taught, every paper published, every institutional role accepted reinforced the appearance of normalcy. This normalization was itself a form of contribution. At the same time, refusal to work risked imprisonment, execution, or the replacement of expertise with ideological incompetence that could cause even greater harm. Fear played a central role, but fear alone does not explain the choices made. Many scientists were deeply attached to their work, their students, and their national scientific traditions. For German physicists, the idea of abandoning Germany meant more than exile. It meant severing themselves from a cultural and intellectual identity shaped over generations. The regime weaponized this attachment, framing departure as betrayal and endurance as patriotism. The moral tension intensified as war progressed. Scientific work became increasingly entangled with military objectives. Even research that appeared theoretical or defensive could be repurposed for destruction. Scientists were often kept deliberately ignorant of final applications, allowing them to maintain a sense of moral distance. This compartmentalization made it possible to continue working while avoiding direct confrontation with the consequences of one's labor. Silence became a survival strategy, public dissent was suicidal, private doubt was widespread, and moral conversations were pushed into whispers, diaries, or coded language. In this atmosphere, the absence of protest does not necessarily imply agreement, but it also does not absolve responsibility. The regime depended on this silence. It thrived not only on fanaticism, but on accommodation. After the war, this moral ambiguity became the subject of intense scrutiny. Scientists who had remained were forced to explain themselves to victors who benefited from similar compromises under different flags. Many defended their actions by arguing that science itself is neutral, that responsibility lies with political leaders, not researchers. Others claimed they acted to prevent worse outcomes, to slow progress, or to preserve knowledge for a future beyond tyranny. These justifications reveal the central ethical dilemma. Can intent outweigh outcome? If a scientist remains in a criminal system believing they are limiting harm, but their presence nonetheless strengthens that system, how should history judge them? Moral philosophy offers no consensus. Consequentialist arguments clash with deontological ones. Survival ethics collide with ideals of moral purity that are easier to uphold in hindsight than under threat. What makes this dilemma enduring is its universality. The Nazi regime represents an extreme case, but the core question transcends that context. How should individuals act when all available choices are compromised? Is withdrawal always moral, even if it leaves power in worse hands? Is participation always immoral, and that prevents CSCUL ATPRODUCTSTSO that PHE? These questions resist definitive answers because they arise in situations where moral clarity has been deliberately destroyed. The danger lies in simplifying the past into comforting narratives. Casting all who stayed as villains ignores the coercive reality of dictatorship. Casting them as secret heroes risks excusing complicity. The truth exists in the uncomfortable space between these extremes. It requires acknowledging that ordinary human motives, fear, pride, loyalty, ambition operate even under extraordinary evil. Working under the Nazi regime forced scientists to live with unresolved moral tension. Many carried that burden for the rest of their lives, whether publicly acknowledged or privately endured. Some emerged defiant, others defensive, others silent. Their stories challenge the idea that morality is tested only by grand gestures. Often, it is tested by daily decisions made under pressure, where every option is flawed and delay itself becomes a choice. This moral ambiguity is not a historical curiosity, it is a warning. It shows how easily expertise can be absorbed by power, how quickly neutrality collapses under authoritarianism, and how fragile ethical frameworks become when survival is at stake. The legacy of those who worked under the Nazi regime is not a verdict, but a mirror. It reflects the uncomfortable truth that in extreme systems, the line between resistance and complicity is rarely clear, and judging it requires humility as much as judgment. The German uranium project emerged not from a single grand vision, but from a moment of scientific shock. In late 1938, the discovery of nuclear fission revealed that the atom contained energies far beyond anything previously imagined. What followed in Germany was not an immediate rush toward an atomic bomb, but a cautious, fragmented attempt to understand what this new phenomenon meant. The project was shaped as much by confusion, skepticism, and bureaucracy as by ambition, and this reality is essential to understanding its true scientific goals. Unlike later narratives that portray the German effort as a mirror image of the Manhattan Project, the uranium project never began with a clear mandate to build a weapon of mass destruction. It started as an exploratory research initiative, driven primarily by physicists seeking to understand whether nuclear fission could be controlled, sustained, and possibly harnessed for energy. The earliest meetings were academic in tone, filled with theoretical discussions rather than military urgency. This was science probing its own boundaries, not yet a race toward apocalypse. The structure of the project reflected this uncertainty. Responsibility was scattered across different institutions, including the Army Ordnance Office, universities, and research laboratories. There was no centralized authority equivalent to what later existed in the United States. Funding was limited, priorities shifted frequently, and military leaders lacked the scientific literacy to impose a focused direction. In this fragmented environment, the project evolved slowly and unevenly, guided more by feasibility than by ideology. At its core, the German effort focused on the possibility of a nuclear reactor rather than a bomb. A reactor promised controlled energy release, something that aligned more comfortably with existing industrial and scientific frameworks. The concept of an atomic bomb requiring rapid, uncontrolled chain reactions and vast quantities of enriched material, seemed to many involved as technically distant and economically unrealistic. This assessment shaped the project's goals in profound ways. Scientific calculations played a decisive role. Early estimates suggested that an atomic bomb would require an enormous amount of purified uranium-235, far more than Germany could realistically produce during wartime. Isotope separation was known to be extraordinarily difficult, energy-intensive, and slow. Germany lacked both the industrial capacity and the political will to divert massive resources into a project whose outcome was uncertain and whose timeline extended beyond the expected duration of the war. As a result, the uranium project prioritized experiments with heavy water and natural uranium. The aim was to determine whether a self-sustaining chain reaction could be achieved under controlled conditions. This was reactor physics, not weapons engineering. Laboratories focused on neutron moderation, absorption rates, and reactor geometry. These were foundational questions, essential for any nuclear technology, but they did not move directly toward a bomb. The political context reinforced this direction. Adolf Hitler and much of the Nazi leadership were deeply skeptical of theoretical science. Abstract mathematics and invisible particles did not align with their world, which favored tangible, immediate weapons like tanks, rockets, and aircraft. When presented with assessments that nuclear weapons would not be available in the near term, leadership interest waned. Resources flowed instead to projects with quicker military payoff, such as the V-2 rocket program. This lack of enthusiasm from the top created a paradox. On one hand, it limited the project's scale and urgency. On the other, it gave scientists a degree of autonomy. Without intense pressure to deliver a bomb, researchers could frame their work in more conservative, energy-focused terms. The uranium project became, in practice, a scientific investigation into nuclear possibilities rather than an all-out weapons race. It is also important to recognize the internal skepticism among the scientists themselves. Many doubted whether a bomb was feasible at all under wartime conditions. Some questioned whether it was even theoretically achievable with known physics and available materials. Others were more concerned with understanding fission as a phenomenon than exploiting it militarily. This diversity of perspectives meant there was no unified drive toward weaponization. The project's experiments reflect this reality. Reactor assemblies were built in laboratories and caves, not massive industrial complexes. Measurements were careful and incremental. Failures were common, progress was slow, and results were often ambiguous. There was no equivalent of large-scale uranium enrichment plants, no vast workforce dedicated to isotope separation, and no sustained push toward explosive design. This does not mean the possibility of a bomb was ignored entirely. Theoretical discussions did address critical mass and chain reactions. Scientists were aware, at least in principle, that a weapon was possible. But awareness is not the same as pursuit. In the German context, the bomb remained a distant theoretical endpoint rather than an operational objective. The gap between knowledge and action was never bridged. By the later years of the war, the uranium project had effectively settled into a defensive posture. Its primary scientific goal was understanding and containment rather than acceleration. Reactor research continued, but without the scale or urgency required to change the course of the war. The project survived, but it never dominated Germany's scientific or military strategy. This reality became starkly clear after the war. When German scientists learned of Hiroshima, their reactions were not those of rivals narrowly beaten to the finish line. They were shocked, confused, and unprepared. The speed and scale of the American success revealed how limited the German effort had been. It was not merely a failure of execution. It was evidence that the project had never truly aimed at the same target. Understanding the German uranium project requires abandoning the assumption that all nuclear research during the war was bomb-driven. In Germany, it was not. It was shaped by skepticism, limited resources, ideological distrust of abstract science, and a scientific culture that emphasized caution over ambition. Its goals were exploratory rather than transformative, defensive rather than revolutionary. In this sense, the project stands as a case study in how political priorities shape scientific outcomes. The physics of fission was universal, but the interpretation of its potential was not. Where one nation saw an existential race, another saw an interesting but impractical curiosity. The consequences of that difference reshaped the modern world, leaving the German uranium project not as a failed bomb program, but as a restrained scientific inquiry overshadowed by what might have been. Werner Heisenberg's alleged resistance during the war has become one of the most debated aspects of his legacy, precisely because it exists in the space between intention and evidence. There is no dramatic manifesto, no recorded act of open defiance that clearly establishes him as a resistor. Instead, what exists are patterns, choices, and silences that suggest a more subtle form of opposition, one that relied not on confrontation but on restraint. Central to this debate are the scientific decisions Heisenberg made while advising Germany's nuclear research efforts. His calculations regarding the feasibility of an atomic bomb emphasized difficulty, scale, and delay. He consistently portrayed the bomb as a distant possibility, requiring resources far beyond what wartime Germany could provide. Whether these assessments were honest miscalculations or deliberate downplaying remains unresolved, but their effect was unmistakable. German leadership did not prioritize the bomb, and resources were never mobilized on a scale that could have made it possible. Some historians argue that Heisenberg genuinely misunderstood critical aspects of bomb physics during the early years of the war. They point to errors in his estimates of critical mass and isotope separation as evidence of technical confusion rather than moral choice. Others counter that these errors are inconsistent with his demonstrated brilliance. They note that Heisenberg was fully capable of reconstructing correct calculations later, raising the possibility that earlier pessimism was strategic rather than accidental. Heisenberg's approach to reactor research also feeds into this interpretation. He focused on controlled chain reactions, emphasizing stability and moderation. This path naturally diverted attention away from explosive applications. Reactor physics is not a shortcut to a weapon. It is a different road entirely. Choosing this direction framed nuclear research as a long-term scientific endeavor rather than an immediate military solution. Equally telling are Heisenberg's interactions with political and military authorities. He did not dramatize nuclear potential, nor did he lobby aggressively for funding or industrial expansion. In a regime that rewarded enthusiasm and results, his cautious tone stood out. He spoke the language of uncertainty and limitation, not of promise and power. This posture discouraged urgency and allowed the project to remain marginal within Germany's war priorities. The Copenhagen meeting with Niels Bohr remains the most emotionally charged episode in this story. Heisenberg's attempt to discuss nuclear ethics, however clumsy or ambiguous, suggests a man wrestling with moral responsibility. Bohr interpreted the conversation as a threat or a warning. Heisenberg may have intended it as a signal of restraint. The tragedy lies in the miscommunication itself, revealing how even shared scientific language could not bridge the moral abyss created by war. Silence also plays a role in the interpretation of resistance. Heisenberg did not publicly celebrate Nazi ideology. nor did he participate in its racial rhetoric. He defended modern physics against ideological attacks, insisting on its scientific validity even when doing so endangered his career. This defense was not heroic in the cinematic sense, but it required courage in a system that punished deviation. Critics argue that such actions fall short of true resistance. They point out that Heisenberg accepted state positions, benefited from protection, and continued working while others suffered or fled. They argue that restraint within a criminal system does not erase participation in it. These critiques are valid and necessary, reminding us that resistance is not defined solely by intent, but by impact. Supporters counter that Heisenberg's influence may have prevented catastrophic outcomes. By shaping the scientific narrative around nuclear impossibility, he reduced the likelihood that Hitler would gain access to a weapon capable of unimaginable destruction. If this was deliberate, it represents a form of resistance that operated within the system rather than against it. The problem is that such resistance leaves no clear trail. It is invisible by design. It relies on understatement, delay, and ambiguity. History struggles to evaluate actions that were meant not to happen rather than achievements that did. The absence of a bomb cannot be conclusively attributed to moral choice, yet neither can it be dismissed as mere incompetence. Heisenberg's alleged resistance forces us to confront an uncomfortable reality. Moral action under tyranny often looks like compromise rather than defiance. It may involve choosing the lesser evil, slowing progress rather than stopping it, and preserving knowledge rather than openly opposing power. Whether this deserves praise or condemnation depends largely on how one weighs intention against outcome. In the end, Heisenberg's wartime choices resist definitive judgment. They reflect a man navigating a world where every path was tainted, and where the most consequential decisions were made quietly, behind closed doors, in the language of equations rather than slogans. His story challenges the expectation that resistance must always be visible, and it leaves us with a question that remains unsettled. When catastrophe is avoided, does it matter how or why? The clash between Nazi ideology and modern physics was not a minor academic disagreement. It was a fundamental conflict between two incompatible ways of understanding reality. At its core, modern physics was built on abstraction, uncertainty, probability, and mathematical formalism. Nazi ideology, by contrast, demanded simplicity, certainty, hierarchy, and ideological obedience. This collision placed physics itself on trial, turning scientific truth into a political liability. Quantum mechanics and relativity undermined the classical world. That the regime found emotionally and ideologically comforting. These theories rejected determinism and absolute certainty, replacing them with probabilities, observer dependence, and limits to knowledge. For a regime obsessed with control, purity, and rigid order, such ideas were deeply unsettling. The very notion that nature was not fully predictable contradicted the authoritarian belief that the world could be mastered through will, discipline, and racial destiny. This discomfort quickly became hostility. Influential figures promoted the idea of German physics, a movement that rejected relativity and quantum mechanics as alien, abstract, and allegedly Jewish. Scientific merit was replaced by racial and ideological criteria. Mathematics was portrayed as suspiciously detached from physical intuition, and theoretical work was attacked as decadent speculation rather than practical knowledge. Physics was no longer evaluated by experiment or consistency, but by whether it aligned with nationalist myth. The consequences were devastating. Some of the greatest scientific minds of the century were forced into exile, stripping Germany of intellectual leadership almost overnight. Entire research traditions collapsed, laboratories lost mentors, students lost teachers, and scientific continuity was shattered. What had once been Germany's greatest strength became a self-inflicted wound. The regime's attempt to reshape science in its own image weakened the very technological superiority it sought to achieve. Yet modern physics did not disappear entirely. It survived in pockets of resistance, maintained by those who understood that abandoning rigorous theory would mean abandoning science itself. Defending quantum mechanics under these conditions was not simply an academic preference, it was an act of defiance against ideological intrusion. To insist that equations mattered more than slogans was to assert that nature did not bend to politics. This tension exposed a deeper truth about authoritarian systems. They fear complexity. Modern physics thrived on complexity, paradox, and counterintuitive results. It required humility before evidence and acceptance of limits to human control. Nazi ideology demanded the opposite. It claimed absolute answers, moral certainty, and the supremacy of will over reality. Where physics revealed uncertainty, ideology demanded obedience. The irony is that the regime simultaneously depended on science for its military ambitions. Advanced weapons, radar, rocketry, and communications all required cutting-edge physics. This created a contradiction that could not be resolved cleanly. The state needed scientific expertise while distrusting the intellectual foundations on which that expertise rested. As a result, scientists were tolerated rather than embraced, valued for results but mistrusted for their methods. This contradiction shaped how physics was practiced. Researchers learned to frame their work carefully, emphasizing practical outcomes while downplaying theoretical implications. Abstract discussions were confined to lecture halls and private conversations. Language became cautious. Ideas were expressed in ways designed to avoid ideological scrutiny. Science adapted not by changing its truths, but by disguising them. The conflict also revealed how fragile scientific institutions can be when truth is subordinated to power. Once ideology gains authority over knowledge, progress becomes conditional. Research advances only when it serves doctrine, and errors persist when they align with belief. The Nazi attack on modern physics stands as a warning of how quickly intellectual achievements can be undone when political loyalty replaces empirical validation. At the same time, the survival of modern physics within this hostile environment demonstrates its resilience. Equations continued to work regardless of who denounced them. Experiments produced the same results regardless of ideology. Nature did not cooperate with propaganda. This quiet indifference of reality to human belief became the ultimate refutation of ideological science. By the end of the war, the contrast was undeniable. The regime that claimed supremacy over nature had failed to harness one of the greatest scientific revolutions of its time, while those who embraced theoretical abstraction achieved unprecedented technological power. The victory of modern physics was not merely scientific, it was philosophical. It affirmed that truth cannot be legislated and reality cannot be reshaped by ideology alone. This conflict leaves a lasting lesson. Science flourishes where doubt is permitted, questions are encouraged, and conclusions remain provisional. It withers where certainty is enforced and inquiry is constrained by belief. The struggle between Nazi ideology and modern physics was not only about equations and experiments, it was about whether reality itself could be subordinated to power. History answered that question decisively, but only after immense human and intellectual cost. The end of the war did not bring clarity to Werner Heisenberg's actions. It intensified the uncertainty surrounding them. In the summer of 1945, Heisenberg and several other leading German scientists were taken into Allied custody and transported to a country house in England known as Farm Hall. There, under comfortable but constant surveillance, they became subjects of an experiment designed not in physics but in truth. Unbeknownst to them, every conversation was secretly recorded. The goal was simple: to discover what the German scientists had truly known, attempted, and believed during the war. When news of Hiroshima reached Farm Hall, the reaction was immediate and raw. The scientists were stunned. There was disbelief, confusion, and a profound sense of shock. Some initially assumed the bomb must have been a bluff or a propaganda exaggeration. The scale of destruction seemed incompatible with what they believed possible. This moment revealed a crucial fact. The German scientists had not expected an atomic bomb to be built so quickly, or perhaps at all. Heisenberg's response was particularly revealing. In the first hours after hearing the news, he struggled to explain how such a bomb could work. His initial explanation contained errors, suggesting either a genuine misunderstanding or a mental block shaped by years of dismissing the bomb as impractical. This moment has been cited by critics as proof that he simply did not understand bomb physics during the war. Yet the story does not end there. Within days, Heisenberg reconstructed the correct theoretical explanation. He outlined how a bomb could be built, including the principles of critical mass and rapid neutron multiplication. This sudden clarity reignited the debate over his wartime role. How could someone capable of such insight have failed to grasp it earlier? Was his earlier confusion authentic, or was it the residue of years spent convincing himself and others that the bomb was unattainable? The Farm Hall transcripts do not provide definitive answers, but they offer invaluable insight into the mindset of the German scientific elite. They reveal men who were intellectually brilliant, morally strained, and deeply conflicted. There is no triumphant regret at having failed to build the bomb, nor is there clear relief. Instead, there is a mixture of wounded pride, moral unease, and quiet rationalization. One striking feature of the conversations is the absence of overt ideological enthusiasm. The scientists did not express loyalty to the fallen regime, nor did they speak as defeated conspirators lamenting lost power. They spoke as professionals trying to understand what had happened and what it meant for their own responsibility. This tone complicates simplistic narratives of fanaticism or innocence. The transcripts also expose a subtle self-defense mechanism. Several scientists emphasized that they had never seriously attempted to build a bomb, framing their work as reactor research rather than weapons development. This insistence may reflect genuine belief, or it may reflect an awareness that they were now being judged by the victors. The boundary between explanation and justification is thin, and Farm Hall captures that tension in real time. For historians, the recordings are both a gift and a frustration. They offer candid conversations, but not confessions. They reveal thought processes, but not intentions. Silence, hesitation, and contradiction appear as often as clarity. What emerges most clearly is uncertainty itself. The scientists were not unified in their interpretations of the past, and Heisenberg was not portrayed as a commanding figure who had led a secret moral rebellion or a failed weapons race. The post-war investigations extended beyond Farm Hall. Allied interrogators sought to determine whether Germany had been close to building a bomb and whether Heisenberg had deliberately held back. The conclusion was that Germany had not been close. Industrial capacity, political priorities, and scientific focus had all worked against rapid progress. Whether moral choice played a role remained unresolved. For Heisenberg, the post-war years were marked by a careful reconstruction of reputation. He returned to a Germany eager to rebuild intellectually and morally. He became a leading figure in restoring scientific institutions, advocating peaceful uses of nuclear energy, and reflecting publicly on ethical responsibility. Yet he never fully resolved the questions surrounding his wartime actions, nor did he attempt to close the debate definitively. The farm hall revelations did not deliver a verdict, they deepened the mystery. They showed that Heisenberg was neither a simple villain nor a hidden hero. He was a man shaped by circumstance, constrained by power, and burdened by choices whose consequences he could not fully control. The recordings preserve a rare moment when history speaks without knowing it is being watched, leaving behind not answers, but echoes of doubt that continue to define Heisenberg's legacy. Controversy surrounding Werner Heisenberg has endured not because new evidence keeps emerging, but because his story refuses to settle into a moral conclusion that feels satisfying. Decades after the war, historians, physicists, and ethicists continue to argue over whether he should be remembered as a man who failed to deliver a weapon to a murderous regime, or as one who simply failed. This unresolved tension has become part of his legacy, shaping how science remembers itself when confronted with power. One reason the debate persists is that Heisenberg's actions can be interpreted through multiple, equally plausible lenses. Viewed through a technical lens, Germany did not build an atomic bomb because it lacked industrial capacity, centralized coordination, and sustained political commitment. From this perspective, Heisenberg's role appears secondary, constrained by systemic limitations rather than personal choice. Viewed through a moral lens, however, his influence as the leading physicist suggests that what he emphasized, calculated, and advised may have redirected history away from catastrophe. The idea that Heisenberg saved physics operates on two levels. On the most literal level, it refers to the preservation of modern theoretical physics within Germany during a period of ideological hostility. By continuing to teach quantum mechanics and defend its legitimacy, he prevented its complete eradication from German intellectual life. When the war ended, this continuity allowed scientific reconstruction to begin without starting from zero. In this sense, physics survived not because the regime supported it, but because it endured quietly in spite of it. On a broader level, the phrase suggests that physics itself was spared a moral collapse. Had Nazi Germany developed and deployed nuclear weapons, the relationship between science and evil would have been altered irrevocably. The atomic bomb already forced humanity to confront terrifying ethical questions, but its use by a genocidal regime would have tied modern physics even more directly to systematic annihilation. Avoiding that outcome, whether by choice or circumstance, mattered deeply to the moral history of science. Critics argue that this framing risks granting Heisenberg credit for what did not happen. They caution against moral hindsight that transforms absence into heroism. The failure to produce a bomb can be explained without invoking conscience, overstating his restraint risks, minimizing the suffering caused by the regime he lived under and worked within. It also risks creating a comforting narrative in which great minds are secretly virtuous, even when surrounded by atrocity. Supporters counter that history is shaped as much by prevention as by action. Not all responsibility leaves visible traces. Delays, understatements, and refusals to exaggerate potential can alter political decisions profoundly. If Heisenberg consciously chose not to accelerate nuclear weapons development, even knowing it could cost him favor or influence, then his contribution lies precisely in what he did not do. What makes this controversy especially powerful is that it forces science to confront its own vulnerability. Scientific knowledge does not exist in isolation. It moves through institutions, funding structures, and political agendas. Heisenberg's story demonstrates that scientific brilliance does not guarantee moral clarity, and moral intention does not guarantee moral outcome. The same equations can lead to energy or annihilation, depending on who controls them. His legacy also challenges the idea of moral purity. Many would like history to offer clear examples of resistance or guilt. But Heisenberg occupies the uncomfortable middle ground. He neither fled nor fully embraced the regime. He neither built the bomb nor openly sabotaged the effort. This ambiguity mirrors the reality faced by many under authoritarian systems, where choices are constrained and consequences are unpredictable. In the decades after the war, Heisenberg became an advocate for peaceful science and international cooperation. He spoke about responsibility, restraint, and the dangers of unchecked technological power. Some see this as genuine reflection shaped by experience, others see it as an attempt to reshape memory. Both interpretations may contain truth. Human beings often seek meaning in their past, especially when that past cannot be undone. Ultimately, the question of whether Heisenberg saved or failed physics may be unanswerable, and perhaps that is the point. His story resists closure because it exposes the limits of moral judgment applied from a distance. It reminds us that history is lived forward but judged backward, often without access to the fears, pressures, and uncertainties that shape decisions in the moment. What remains undeniable is that Heisenberg's life sits at the intersection of scientific genius and historical catastrophe. His legacy is not a verdict but a challenge, asking future generations of scientists to consider not only what they can do, but what they should choose not to do when knowledge meets power.